Hello everyone, this is Dr. Khalid, and today we are extending our discussion on alkyl halides. So, in this lecture, we are talking about chemical reactions. So, when we talk about the chemical reactions, and as we will proceed, how to prepare the alkyl halides and what are the different reactions that alkyl halides undergoes. So the first thing which we need to explore is that what are the type of bondings, what are the bond cleavage, what is the bond dissociation energy. So we should know about that how the halide bonds, what is the alkyl halide bond strength is, and what are the different reaction conditions, possible reaction conditions by which we can conduct some of the reactions and we can transfer from one uh, a class of the compounds to another one. So the first thing which we need to know about alkyl halides in comparison to the hydrocarbons is this one, that apart from the CF, which is the carbon, any of the hydrocarbon which has the halogen F, which has replaced one of the hydrogen, and now we have the fluoro or the fluorine based alkyl halide. So apart from this one, and that is the exception, the CX bonds are weaker than the CH. So that may be surprising for some of you, and some may get that point that why we are saying that these bonds are weaker than CH bonds as measured by bond dissociation enthalpies, which is called the BDE, bond dissociation energy. So I will talk about that why we are saying that the CX bonds are weaker than the CH, though we may think that the CX is the highly electronegative, so this is keeping that electron pair towards itself. So they have the very good attractions, the partially positive and the partially negative. And while we compare the CH bond, so they have not that larger electronegativity difference. And the good thing is that that reason is basically behind uh, this bond strength or the bond weakness of the CX versus CH. So the bond dissociation enthalpy is defined as the amount of energy required to break a bond homolytically into two radicals in the gas phase at 25 degrees C. It's at room temperature, standard temperature. So the bond dissociation enthalpy or the BDE is basically the amount of energy which we require to break a bond homolytically. I will explain though in more detail, but the homolytically, as the name state, is that that breakage is with the equal share. So means whatever the atoms were combining here, so they are after sharing the same number of electrons after the cleavage of that bond, which was initially in between them. So then by taking this share, they will have the unpaired electrons, and that unpaired electron species is termed as radical in the gas phase at 25 degrees C, because these reactions are happening in when this bond dissociation energy it actually means is, so that is happening when they are converting into the gaseous phase, and uh, that is a standard energy, right? So there are the different ways to determine that bond dissociation energy, and that is a virtual one, though that is experimentally is not measurable. So there are the other indirect ways how we can find out the bond energy of the reaction and the bond dissociation, so through the hydrogenation, through the heat of combustion. So in most of organic chemistry books, you can see in the appendix there are the tables which have provided with the different bonds and their associated bond energies, and then from these energies, what are the bonds formation, what are the bond breaking, you can easily calculate the bond energy, the energy of the reaction, that either that is the endothermic or either that is the exothermic, by combining all of the energies of the bond formation and the bond dissociation or the breaking of the bond, right? So here you can see this is an example. So this is the CH3, which is showing you the one of the alkyl side of the haloalkane, and this is X is for any of the halogen. That could be the chlorine, bromine, iodine, and fluorine. Experimentally, when we talk about the laboratory preparations of the fluorine haloalkanes, so we mainly talk about the chlorine and bromine because these are controllable and these are more viable reactions which we can perform in the laboratory. I will explain later that why we have the restrictions with the fluorine and the iodine. Well, that X could be any of the halogen. So when that this mark is showing that we are providing some kind of energy, that could be the light, that could be the thermal energy, and we are breaking that bond, right? So if that bond is breaking in that form, that this bond means there is a pair of electron. So whenever we talk about that this is the pair, a bond, so this bond means that there is a pair of electron. So each electron is sharing with each contributed atoms which are forming the bond, because that is a covalent bond. This is not the ionic one. So in covalent bond, this is through the mutual sharing, right? So this bond means there is a pair of electrons, and when it cleave homolytically, means that is cleaving in that way that this CH3 is getting one unpaired electron and this X is getting one unpaired electron. So that is the homolytic cleavage of that bond. So for showing these one, so this is basically the bond length and the bond strength and how the bond are breaking, and then they are forming the radicals, right? So as I am telling you that the bond, homolytic bond cleavage is when they are breaking in a form that each contributing atom is taking the equal share. Heterolytic bond cleavage is that one in which the cleavage of a bond is in that way that the fragments retain both electrons. One fragment retain both electrons and the other has none, right? It means there is the unequal share after the breaking of the bond. So one is carrying the full pair of electrons, that will get the negative charge, and which is the deficient in electron after the bond cleavage, so that will get the positive charge. So here we can see the example. So this haloalkane bond can be broken in two ways. So this homolytic cleavage is in a way when they both carbon and X which were forming that bond. So here this bond is actually in between the carbon and the X. So this is just for the simplification. This has written as a CH3 on that side fronting to the X. So this methyl radical is there, and this is getting the unpaired electron. X is in a radical form. Now in heterolytic cleavage, we get the ions. So this is the carbocation, and this is the X negative, which is the another one is one is the cation, another one is the anion one, right, which is the negatively charged, and that is in excess of electrons. So I have to show one thing which is very important, and you need to pay attention towards that, that when we are writing this is homolytic cleavage, so we use the fish hook arrow. Fish hook arrow is the one, or you can say the half arrow, or the one, not a complete arrow. So we are just showing the half arrow. It is just a one-sided, not on the both sides. We draw like this. A proper arrow is like this one, right? So I'm just drawing the half one. So this is called the fish hook arrow. We call it a fish hook arrow, right? And you should know that one, that if that mechanism of the reaction is through the homolytic cleavage, so you have to draw with the fish hook arrow. And if that is through the homolytic cleavage, then you will draw the straight arrow, right? So in a fish hook arrow, So always you know that whenever we are drawing the mechanism, so the tail of the arrow is from at the side where this electronic bond is, which is a source of the electron, and that head is towards that side where it will go and where that electron will jump or contribute to the site, right? So now after the homolytic cleavage, that is the methyl radical and there is the halide radical. um, Now for the case of the heterolytic cleavage, right? So what I have to do is that now I will draw the full arrow to show that this electron pair is moving towards the X while keeping leaving that methyl as electron deficient. So that's why it is carrying the positive charge at the end when that bond has cleaved. So the X is getting the negative charge, right? So here we are drawing this arrow in a form. So we just draw the banded form according to where the structure is and how to mention the movement of the electron, right? So this is the full arrow to show the heterolytic cleavage. I hope you got that point. So now for the next thing, this is a table, and this is to demonstrate to you that you can compare the bond length versus the bond dissociation enthalpy for each of the halogen. Now you can see that the carbon hydrogen bond is the 109 pm. That is the distance between that carbon and hydrogen bonding. So its bond dissociation enthalpy means energy required to break that bond is 414 kilocalories, or the kilojoule we can mention in alternatively. So the kilojoule, it's a 414, and if we mention that in the kilocalories per mole, so that is the 99. So if we compare with the CH and we can see the halogen cases, so this is a straightforward for the carbon hydrogen, right? So that's why the carbon hydrogen bond is harder to break as compared to the halogen one. So that's why the people and the researchers are now more into exploring the CH functionalization and the bond breaking uh, by using the different method and the strategy. So it's also another very diverse and the challenging field. The people are working in the synthetic chemistry, and they are exploring these bond breaking and the functionalization. So if you compare with the CF, this is a carbon and fluorine, and we know that among the halogen, the fluorine is of the teeny size as compared to the chlorine, bromine, and iodine. And the iodine is a huge in its size and its volume as compared to rest of the halogen one. So the CF having the highest electronegativity in the halogen group and smaller in size. So the bond length is 142 picometer, right? It is greater than the 109, but less than the rest of the halogen alkyl halides. So the value of the bond dissociation is greater than this CH bond, right? So this is the 464. Now, the question is this one, that this is the 109, this is a shorter in length, right? And this is the bigger in length, right? So, how we can see that one? So, the picometer is a very small unit when we talk about this one. So, the energy here for the CF is greater in as compared to the hydrocarbon is because this F is tiny, this is highly electronegative, and the bond length is smaller as compared to the rest of the alkyl halides. So that's why there is no partial, there is no great, good electronegativity difference. So they have the very minor electronegativity difference. So there is less attraction as compared to the CH bond, right? So the CF is demanding the higher energy for the bond association as compared to CH. Now, if we compare the CCl, CBr, and Ci bond, so here you can see that gradually the bond length is increasing. It means the distance between the carbon and the halogen is increasing. And as the size of the iodine is reached at the highest size as compared to the chlorine and bromine, so there is more polarizability. So this bond is much weaker because these electrons are not attracted with the nucleus as strongly as in case of the bromine and chlorine. So that's why this is the demanding the low energy to for the dissociation of that bond. Now the preparation of haloalkanes by halogenation of alkanes. So I will mention, I will tell you that how you can prepare the haloalkyl alkanes or the alkyl halides by different ways. So there is a very straightforward, the simple way for the preparation of the alkyl halide is through the addition reactions, that we can treat any of the alkene which has a double bond, and we can react it with the HX or the halogen. HX means any of the halogen acid, or any of the halogen like the Cl2, Br2, or I2, and that can simply add it to the alkene, and that will convert into the alkyl halides, because wherever there is a pi bond, so there will be the addition of hydrogen and the halogen. Or if we are treating with the Cl2 or Br2, so then there will be the two uh, BR, there could be the conventional, if we are using it in a high amount and a high moles, so then we can go for the di-substituted alkyl halides even. The second method we can prepare is by the replacement of a OH group of the alcohol by halogen. So if we treat the alcohols with the halogen, so that can also give the alkyl halides or the haloalkanes as a product. That reaction is termed as a substitution because we are replacing the one of the functional, a group of atom or the atom by the halogen. So that is a substitution. And the first one was just addition reaction. Now the third one is many of the simpler molecular, low molecular weight haloalkanes are prepared by the halogenation of alkanes, illustrated here by treating 2-methylpropene with bromine at an elevated temperature. And that is again the type of under the classes of reaction or the types of reaction, and that is termed as the substitution reaction. Now emphasis is on the third method. We will explore the halogenation of alkanes. Why? The first reason is this one, that in the industrial scale, the alkyl halides are mostly, they are prepared by the halogenation of the alkanes. The reason is this, that we extract these alkanes as a natural sources from the petroleum product byproducts. So through the fractional distillations, these are the alkanes which we obtain in a good amount, so they can, this is a more economic approach to treat the alkene with the halogen to synthesize the alkyl halide. Another way is the synthetic and mechanistic approach, that when the addition reaction, of course, we can discuss that in the further alkene chapter, and you may have gone through that addition reaction if you have opted the Chem 160 course. And this is the alcohol reactions, and basically the alkenes are not in a domain. And secondly, we wanted to explore the detailed mechanism which we can explore in the halogenation of the hydrocarbon, that how the hydrogen is replacing or substituted with the bromine one. So it's not the simple addition reaction. So definitely there is a substitution. And in this course, we will talk about the substitution and elimination reactions. So in that context, we are mainly focusing on the preparation of the haloalkane by the third method, by using the alkanes or the hydrocarbons as a starting material, for the halogenation and then converting that alkane into the alkyl halide. So here in this example, which I have quoted here, so this is a branched hydrocarbon. This is a branched alkane, and its name is 2-methyl propane. So 1, 2, 3, and this is the longest chain, and at the second position there is a methyl group. So this is the 2-methyl propane, and its common name is isobutane because this is a branch, and in total they are the 4 carbons we can name as isobutane as well. So the bromine, because this is a reactive one, so this do exist in a molecular form. So this is the Br2. Right now we are not using the HBr, but I will ask you and I will discuss if we are using the HBr, so what will happen in that scenario. So Br2, we are using that one. And when it reacts, so an important thing is this one, that don't ignore that reaction condition. So if you are keeping that alkane, that 2-methyl propane and that bromine in a bottle or in a glassware, and you are keeping that in a darkness, so there is nothing is going to happen with that reaction. But when you are applying the light or you're providing heat, so that will give you the substitution reaction, right? So because this CH at a very um, neutral or unreacted reaction condition, so that is not going to be cleaved unless we are providing the thermal or the light energy for breaking that bond and instigating that bromine to attack on that carbon. So here, this Br means this is the Br bond with Br. So I can just write it in open for your understanding. This is the Br, right? So when that bond will be cleaved, right, we are providing that energy to go for this. So it means that has to attack on that C, right? So that could go for the homolytic or heterolytic cleavage, and that we have to decide what is going to be happen with that case. So if it is happening heterolytically, so in that scenario, because these Br have the same electronegativity, so that will cleave the homolytically. So the Br radical and the Br radical, and we will draw the fish hook arrow, right? So then that will combine with this one, and if this is taking again the homolytic through the homolytic cleavage, but if that is the heterolytic cleavage, then that C will be the positive one, and then Br with the negative charge will combine on H1, right? So the homolytic cleavage is more prominent when we are using the HBr, and in a Br2 it goes through the homolytic cleavage, right? So here this Br will get attached to the carbon, and this hydrogen has replaced, and this is bonded with one of the Br. So here, if you name this compound, because now that the compound has changed, that hydrogen from the alkane has replaced with the halogen. So what will be the name of that compound? This is the 2-bromo 2-methyl propane. And the common name of this one is the tertiary butyl bromide, because we have discussed in the nomenclature, in the common names of the alkyl halide, and when we are writing in a trivial or common name pattern, then the halogen is as suffix, and we will mention that alkyl chain as a prefix one. So the tertiary butyl means that this carbon is attached with the 3 alkyl groups, right? Which is attached with the bromine. So this central carbon is attached on the 3 side. So that's why this is the tertiary one. If that is the scenario, it is bonded with the 2. So then that will call the secondary, right? So this is the tertiary butyl bromide, and butyl is for the 4 carbon again, and the byproduct, the second product here is the HBr, which is the halogen acid, H, as that was mentioned here. So HX is basically the halogen acid, HBr. So again, if we have the alkane, so we can treat H with the HBr, so that bromine will get attached to that one, and H will be taken up uh, with that, um, depending on what the molecule you are treating as a starting material. So here, and next thing is, the first example was for the bromo alkanes, and now we'll talk about how we can prepare the chloroalkanes. So of course, for the chloroalkanes, we can use any of the chloro acid or the Cl2. So here, this is the methane, which is called the natural gas. We are using this as a starting material. So CH4, if we treated Cl2 in the presence of heat or the light, so we get the CH3Cl. So one hydrogen from the CH4 has replaced or substituted with the Cl, and we get HCl. So the IUPAC name of this product is chloromethane, and the common name is methyl chloride. Now, what if we have the Cl2 in excess, and we have the methane in the system? So this was the chloromethane, and we still have enough chlorine to react with that one. So then that reaction will continue until all of the hydrogen of that carbon has substituted with the Cl. So we can achieve at the maximum level. So because that reaction is a substitution reaction, and we are giving the suitable reaction conditions, and we have the chlorine or halogen in excess. So why not? It will go for in the form of a chain reaction that it will attain, unless all of the hydrogens are substituted with the Cl. So here we can see, if we continue that with the reaction, so now this is our starting material, which has substituted with one of the Cl. So this methyl chloride or chloromethane, again, it is reacting with the Cl2 in the presence of heat. So there is a CH2Cl2, and that is called dichloromethane. And its common name is methylene chloride plus HCl. Then again, if we continue reacting this with the Cl2, then this is a dichloromethane, and it is a methylene chloride. And when it is treated with the Cl2 in the presence of the heat or the light, so this is a CHCl3 trichloromethane, and this is called the chloroform, one of the most common and very famous organic solvent we use in our laboratory for the number of test teaching labs, synthetic or the experimental setups. So again, if the chloroform continue and we have enough halogen to react with that, so we can get that tetrachloromethane. This is the carbon tetrachloride. It is again also one of the common um, organic solvent you may know present in your organic labs. So you see, now the carbon has substituted all of its hydrogens with the Cl. So now even if we have more halogen in the reaction system, then there is no further effect on that reaction. So that is the ending point, or that is the um, end step, or the termination step, that this is the final product we are getting from that methane. We started from the methane, and with excess of chlorine, we can get the carbon tetrachloride. But we can control that reaction by limiting the halogen amounts. If we control the reaction conditions by keeping any of the reactant under control, so we can even stop at this level, and depending that what is our required or target product we want to prepare. Now, at the end, this is the task for you. We have discussed that in the presence of the light, and there is the halogen. So the alkanes will combine with these halogen to give you the alkyl halide. Now I have set up this question in a way that you have to name and draw structure formulas for all possible monohalogenation product. What I mean with the monohalogenation product is that we can write that end product, that of course if with the excess of the Cl, that can acquire the dichloro. So I'm just limitizing that you just have to mention the monochloro, means the structure with only one halogen substitution. But of course that can be on the different position wherever the hydrogens are there, so that Cl can substitute that hydrogen and that can attack on it. That is our further discussion, which we will discuss in our further lectures, that what is the preference for the halogen, that that product will be in a larger amount and the rest has the low percentage if we are having more than one position where the chlorine can attack. So here, this is the task for you, and for these three, you have to draw the structures of all of the monohalogenated products. So I'm again emphasizing that you have to keep in your mind that this is a line structure, and you should know that wherever there are the hydrogens, so you can just place one Cl and then again assign and select the longest chain and the position to name that one. A hint is this one: wherever there are the different IUPAC name in terms of the position, like for example, in one case you are getting this the 2-chloro, in one case you are getting this 3-chloro. So these are the two different compounds. So these are the product expected products. But if you are putting one Cl on this terminal and one Cl on this terminal, so when you will start naming and selecting the longest chain, so they may give you the same IUPAC name. So it means this is just the shift of how you're drawing on a paper, but when you have to select the position, so that is the same compound, right? So don't repeat that one. So you have to write all possible different monohalogenation products coming out of these starting material, these alkanes reacting with the halogen one. So that for today, and I hope you get that concept. But still, if you have any query, any question you want to clarify, so I'll happy to help you. You can comment or you can write an email to me, so I would answer you. Thank you so much. Have a good day.